Yeah, now we have seen simple models like logistic regression and more complicated models like multilayer perceptrons. So I think that's a great time now to talk about topics like overfitting and underfitting. So in particular, problems with models that are too simple, like logistic regression, and problems with models that fit the data too well, maybe multilayer perceptrons. So yeah, the big problem with models that are too simple is that, we don't get a good performance out of them. For example, when we used logistic regression on MNIST, we got 93%, whereas when we used now that we have seen a selection of models like logistic regression as a simple model and multilayer perceptron as a, I would say, more complicated model, it's, I think, a good time to talk about overfitting and underfitting. In particular, problems that arise with models that are too simple, like logistic regression applied to MNIST data, and models that fit the data too well, for example, multilayer perceptrons with too many features. So with that, let's talk about some of these topics. But I also wanted to start this video with a small, let's say, quiz. So here I'm showing you some images from the MNIST dataset. And the question is, what image or what number do you think this is? So the true label is actually an 8. The model predicts a 4. I can kind of see how it predicts a 4, though. I mean, if you look at it, it could be almost like something like this, right? So something like this. So it's actually an 8, but it doesn't look that far away from a 4, to be honest. It's actually a pretty tricky case. Or take a look at this one. What would you think this image is? So as you may have thought, it's a 2, but also it's actually not too far away from a 7, right? If you think of a 7 like this, it's actually not too far away. And in fact, that the model predicts a 7 here. Or this one here. What would you think this number here represents? So according to the labels, this is actually a 5. But I also can see how this might be a 3 almost, right? So in that way, another ambiguous case. The last one. So what do you think this one represents? Yep, it's a 6, but also it could be very well be a 0. So like this maybe. Maybe someone was writing the 0 like this. So you can see it's not always very obvious what this number represents. In that way, it's probably even impossible to get a 100% prediction accuracy on that data set. Oops, I have one more example here. So can you think can you guess what these numbers here are in terms of the true labels and the predicted labels? So on the left-hand side, we have a true label 2. On the right-hand side, also a true label 2. So both these numbers represent the digit 2. But you can see they look very different from each other. And also, the model on the left-hand side predicts a 0. On the right-hand side predicts a 7. So here's an overview of some of the failure cases of a multilayer perceptron trained on MNIST. So here I was using a not so good model. It was like a logistic sigmoid activation and output layer. And I used the MSE squared error loss, so I only got 93% accuracy. But that is really besides the point. So the point here is really it's useful to visualize some of the failure cases. So if you train a network on a data set, it's always good to look at the wrong prediction, because sometimes you may also find there's just a mislabeling issue in the data set that you may want to fix. So in that way, sometimes you get additional insights about your data, like issues with your data, by just looking at it. So here it's just interesting to see what the model here predicts. For example, like I mentioned, in Germany we write the 7 like this. In the US it's common to write the 7 like this. In Germany it's common to write the 1 like this. In the US it's common to write the 1 like this. So I can see the model may confuse American 7 with a German 1, for example. I can't see this issue here in this data set, but what I can see is that, for example, this 7 here is mistaken by a 3, because a 3 also has this thingy here in the middle, this little, what would we call it? I don't know. But you can see this is maybe confusing the model, thinking it's a 3 while in truth it's a 7. So here just the bottom line is it's useful sometimes to take a look at your training data set and the wrong predictions. So talking now about overfitting and underfitting. So overfitting refers to the issue when the model memorizes details in the training set that are only very specific to the training set but don't generalize to the test set. So here, for example, what I'm showing you is a plot where I have the error on the y-axis and the model capacity on the x-axis. So what do we mean by model capacity? So with model capacity, I mean in a way the number of parameters or complexity of the model. Think of it for simplicity as the number of parameters, or the ability of the model to fit a complex data set. So a model with more hidden layers compared to a model with fewer hidden layers, a model with more hidden layers has a larger capacity, or a model with wider layers also has a larger capacity to a model compared to a model with fewer or smaller hidden layers. So usually the more layers you have, or the wider the layers are, the higher your model capacity. Alright, so what I'm showing you here now is the training error first. So let's focus on the training error in orange. So the error usually goes down as the model capacity increases. So that means if we have more layers, or, I mean, this is like, of course, not generally true, because then we have issues like vanishing and exploding gradients. So let's say if we have a wider layer, so if we have, let's say, multi-layer perceptron, where this represents our hidden layer. If we make this hidden layer wider, like this, doubling the size, for example, we increase the capacity of that model to fit a complex data set. So usually for the training set, the larger the capacity, the smaller the error. For the test set, though, what we usually observe is first, if we have, so let's say we start with a very simple model here on the left hand side, like only one hidden unit or something in the hidden layer, then the model is too simple to capture the trends or patterns in the training data. So we start with a large error, but then as we make the hidden layer wider, we see that the error goes down. But then let's say we make the layer too large, so too many parameters to learn. What we often observe is that the test set error goes up again, because now the model has so many parameters that it starts memorizing certain patterns in the training set that don't generalize to the training set. So for example, in terms of pattern, like let's say individual positions of pixels, that instead of more the general shape, it would pay too much attention to a particular pixel or something like that. And with generalization error, this is this is like the performance on new data, for example, as measured. Often it's measured via a test set, an independent test set. So we usually use the test set to estimate the generalization error. One more thing, underfitting. Underfitting usually means if the model is not complex enough to capture the trends in the data. So here in this region we can maybe say that this is underfitting. And here on the right hand side this would be overfitting. So overfitting is usually, if you how you would quantify it is usually by looking at the gap between training and test set performance. That is usually one way to assess the degree of overfitting. In practice you will sometimes also hear people saying a model has high bias or a model has high variance. So I want to briefly go over the concept of the bias variance decomposition and how it relates to overfitting and underfitting. However, this is just a very brief rundown. It's not, I would say, the most important thing here in this course. So this course is about deep learning, and because we have only so much time, we won't talk about, let's say, model evaluation techniques in too much detail. There is a simple technique that most people use. I will talk about this a little bit after these slides, and also will show you how that works in code examples. But let's just focus on bias variance decomposition. If you're interested in more model evaluation aspects, I cover more of this in the 451 Introduction to Machine Learning course, which I usually teach in fall semester. But here, because like I said, we only have so much time in deep learning, I don't want to cover this in too much detail here. But I think it's useful to have a basic understanding of what bias and variance means in that context, because you will probably read about this in a paper at some point in your career. So let's say we have a model for regression, because it's simpler in this context. Let's say we have a regression model, and this is some value for a given data point that we want to estimate. Let's say call that value or prediction theta. Let's say this is the true value, and we want to estimate this, let's say by predicting its value using a regression model. And the regression model produces this theta hat here. So theta hat is the prediction. And now, so think of everything here in the context of the squared error loss. So here we talk about the bias variance decomposition of the squared error loss. And now think of having like a large number of training sets. Why we have this large number of training sets is a weird or interesting question. It's like a weird scenario. Usually in practice we only have one training set, but just assume for the sake of this example that we have a very large number of training sets. Let's say we have 1 million training sets. So every time we train a regression model on a training set, we get a slightly different model because the training sets are not identical. So now think of training 1 million models, and each model makes the prediction on the same data point. Let's call this, so the data point corresponding to the theta here, let's call this data point I. This is a prediction for the data point I. And then we average over them. So we average over these prediction for that data point. So here the expectation is over the training sets. So we are predicting the data point for these, using these different models. So then we get this average value here, this expectation, and the difference between this expected value, or this expectation of the theta hat here, of the estimated parameter, the difference between those two, this is our bias. This is how, on average, how far are we off from the true value. In contrast, so the variance, here are just two different ways of writing the variance. You've probably seen that in other statistics courses. But the main point is the variance is defined a little bit differently. It's how spread out these predictions are. So if you have a prediction by a particular model, and then you take the average prediction, so this is really like here, the average prediction, how far or how spread are they? How far are these apart? Squared, so there's no positive or negative value. So how far are they apart? And then taking the expectation. So how far or how scattered are our predictions on average, basically. So because this is like very weird to think about conceptually, I find it easier to have some drawings. So I took this actually from 451. So students who have taken 451 have seen my little drawing here. So that's a person with a bow and arrow, and let's say the person wants to hit some target here. There's also usually some noise around the target, so in the data set. So here, for simplicity, maybe ignore the noise. And the goal is for this person here to hit the target with an arrow. So you can see all the arrows fly short here. So the difference between So this part here, let's say the average here, this would be the expectation in the middle. If you take the average of all these arrows here, this would be the expectation. You can see the difference between this one and this one. This would be the bias. And how scattered or how spread these arrows are, that would be the variance. So why am I explaining this? So usually people relate bias and variance to overfitting and underfitting. Personally, I find it easier to think just of overfitting and underfitting, but yes, some people like to talk about models in terms of bias and variance. So a model with a high variance, if you would train that model with different training sets, this would mean there's a large variety of these predictions of the model. So a model with high variance is also more likely to overfit. And a model with high bias means that it's kind of far off from the target. So in that way, a model with high bias is usually not complex enough. So it's usually underfitting. So high bias is usually underfitting and high variance is usually overfitting. So I try to summarize that here in this plot. So again, we have our error and the model capacity. So the training error and generalization error is what I've shown you before. On the left-hand side, when we have a high error for both training and test data, or high, let's say, high error, surprisingly difficult to talk and write at the same time for me, I don't know why. High error for both training and generalization. Let's say on both training and generalization. It should be, let's say, in terms of both training and generalization error. So if we have a high error, this is usually underfitting. And if we have a high generalization error but a low training error, then this is usually the difference between the green one here, the orange, on the orange one. This is usually overfitting. And variance and bias relates to that. So if we have a very simple model, low model capacity, it usually has a low variance. So even if I fit the model on different training sets, the results are usually quite stable because it doesn't memorize the data too closely. And then the variance goes up as we increase the model capacity. So in that way, the variance increases, and this is usually also correlated to increasing degrees of overfitting. Similarly, with a bias, so a model that is too simple has usually a high bias because it can't fit the data too well. It will always, let's say, do very simple predictions that are always very similar. It's not complex enough to fit the data. And you can see, though, as you increase the capacity, bias goes down. So a high bias model is usually rated to underfitting. So again, for more details, I covered this in 451. But more detail you don't really have to know for this course, for the focus here on deep learning. So like I said, a more detailed understanding is not mandatory for this class. I won't ask you like any more details, let's say in quizzes or exams, than we just covered. So it's just like a brief overview. In practice, there are different ways we can evaluate models. There are, like in 451, there are cross-validation tests. We used bootstrapping and all types of different approaches. Deep learning, when we have very large data sets, we usually use the holdout method, where we have 3 data sets, a training, a validation, and a test set. So that is usually sufficient because we usually have very large test sets, so estimating the performance on a test set should be quite robust, given that we don't reuse our test set multiple times. So the focus is here really that our test set remains independent. So by that, what I mean is usually we have a validation set that we look at when we tune the model. So what we do is usually we fit the model on the training data. Then during training, we look at the validation performance. And then once we are finished, we get the final performance estimate on the test set. That's the usual approach. yeah, and that is something we will also be using in the code examples. So there's nothing really you have to pay particular attention to right now in this class. So for this class, we use this threefold holdout method, which is also common in the context of deep learning if you look at literature. However, if you're interested in more details about model evaluation and best practices, well, we covered this in 451, which you probably either have taken or not taken. You don't have to know any of this for this class, but if you are interested, I have put up an article here on arXiv summarizing basically my lecture notes. This is like different techniques, statistical tests, cross-validation, k-fold cross-validation, bootstrap estimates, and so forth. So yeah, you are welcome to check out this article if you are interested. Yeah, one aspect also about deep learning is that deep learning works best with large data sets. So here I have drawn another conceptual plot related to the generalization error and here the training data set size. So if we have the comparison between traditional machine learning, for example, decision trees, random forests, support vector machines, things like that, compared to deep learning, usually if we have a small data set, traditional machine learning will perform better. So the generalization error for traditional machine learning will be lower. However, as the data set size increases, usually we will find that also traditional methods will perform better. But for deep learning, there's actually a really steep decline of the error with increasing dataset sizes compared to traditional machine learning. So especially deep learning works well with and really even requires large datasets to perform well because we have large models, there are a lot of parameters, and to fit or to parameterize the model well, we need sufficient data. So this is the traditional view. Usually the more data we have, the better. And also this is something, if you find that your model doesn't perform well, you may end up tuning some hyperparameters. You may find that hyperparameter tuning helps with improving the performance a little bit, but there will be probably a point where you can't even make any difference no matter how many hyperparameter values you explore, and that might be a point where more data could be helpful. So, interestingly, I recently saw the paper on double descent. So there was a paper on double descent that came out in December 2019. So that's an observation that is quite interesting and it's quite different from the common belief. So here, what the researchers did is they looked at CNN architecture, standard and ResNets. So standard CNNs and residual networks, both are things we will cover later in this course, and transformers, which we'll also cover at the end of the course. So I'm not sure if that's, the insights here generalize to other models like recurrent neural networks and multi-layer perceptrons, because they haven't looked at those. But at least this was very interesting in the context of CNNs. So all the models were also trained with a cross-entropy loss here. So there is this phenomenon of the double descent. So what does that mean? What does a double descent mean? So here what you can see is like expected. The training error goes down as the model complexity increases. So here you can think of the x-axis as model capacity, which we have looked at before. So that is expected. At some point, though, if we make the model too large, we will see that the error goes up. So here the solid line is the test error. Training error goes still down, but the test error goes up. So this is what we talked about. This is the overfitting. Now the surprise is that it goes up, but at some point it goes down again. So what's going on here? Actually, people don't know quite know yet why this happens. So there are some theories. I will share one of them in a later slide. But so what is interesting here is this double descent, that it first goes down. That's the first descent, and then it goes down again after going up. This is the double descent. So they observed it with 4 different model capacities. So if you make the model larger, you can observe this double descent. And you can also observe it if you train for more epochs. So here again is the test error. They have here on the left-hand side 3 models, a small model, an intermediate model, and a large model. You can see when you train a small model for more epochs, you don't have this. You go basically down, the generalization error goes down. So the model is improving the more epochs we train it. For the intermediate model, you can see it goes down, but then at some point it goes up again. So here the model performs actually worse when we train it longer. So in this case, for this intermediate model, it would be good actually to stop the training early, to stop, let's say, training here. And in the next lecture, I will also talk more about early stopping as a way of regularizing the model, like improving the performance, preventing overfitting. And for the large model, you observe it goes down, then it goes up, similar to the intermediate model, but then it goes down again. So that's also this double descent here. So that's quite interesting. So on the right-hand side is the same visualization, or the same thing, just visualized differently for the model parameter size here on the x-axis and the number of epochs on the y-axis. So there are a couple of thoughts about that from the paper or theories. So at that critical region, so with critical region they mean this region here in the red region, the reason why we may find that it goes up here is that they think it's only one of the models fits the data well and is very sensitive to noise. So with one model, imagine you have a residual neural network, and when you train it, there are many different hyperparameter model weights that you can define to fit the data well. So there are multiple possibilities, and there's only one that fits the data well. There's a particular combination of weights that fits the data well, but it's very sensitive to noise. So if you have small perturbations in a training set as you train, it's very sensitive. It's not guaranteed to find it, and also it's really sensitive to the inputs. So if there's a slight perturbation in the inputs, the model may make the right prediction or wrong prediction, and that way it's not so good in terms of generalizing. But if you have an over-parameterized model, if a model is very large, there are many ways you can fit the data well. So you have a lot of weights, and you only, let's say, maybe need a subset of those to perform well. And there are many different ways you can find a good subset of the weights. And so, they theorize that stochastic gradient descent finds one of these weight combinations that fits the training set well, but also performs well on the test set. So in that way, if I go back, so the claim is basically that here the model that is learned is very sensitive to noise, whereas in this region here, we found a model that performs well on the training set, but also on the test set. There are more experiments in that paper, also experimenting with different degrees of noise. So if you are interested in that, I recommend reading the paper. Here I only took a very small number of figures to just illustrate this double descent phenomenon. So there's also, it's the same as I showed. This is also an interesting figure. It shows both the number of epochs and the width. So there's essentially a model-wise double descent and an epoch-wise double descent. So there are these double descent curves for both different sizes of the model. So if you have more parameters, and also for longer training. Lastly, there's also something they observed with the number of training examples. So if you increase the data set size, there are also some little surprises, but I wouldn't say, so they describe them in the paper as surprises, but I wouldn't say it's a big surprise. The general trend is, so if you have here the error from lowest to highest, so you have the lowest error in this region here where you have a large model and a lot of data, or a small model and a large amount of data. But what is weird is here in between, if you have an intermediate model, more training set size or larger training sets are actually worse compared, or these models are worse compared to the small models and big models. And also when you look at this closely, let's say here, for example, you can see that increasing the number of training examples from here to here improves the generalization error, but then from here to here it becomes worse again, and then it becomes better again. So if you would plot that, you have a, let's say, high generalization error, it drops, and then it becomes worse again. So that is also a little bit weird here. That's some surprise, but in general you can see more training data helps, and also more or larger models perform better. So a good combination is large training set and a large model. So yeah, again, so this is just interesting. If you're interested, you can read about this more. Why this double descent phenomenon happens, I think that is not quite clear. Some people, let's say, I saw in some forums even debate that this might be just some bug in the code or things like that. So many people, though, I can say, have observed this independently, so it's probably a real thing. But why this happens, yeah, that's not quite clear yet. So, but yeah, moving on. So this was just a very brief video. Actually, it was longer than I expected, but still a very brief video in the grand scheme of things, like on overfitting and underfitting. And in the next video, I will show you how we can use multi-layer perceptrons with custom datasets, because so far we only have worked with MNIST, but yeah, chances are for your class project, you will want to work with your own dataset. So with that, in the next video, I will show you how we can do that.